Thank you for tuning in to This Automation Life, brought to you by Brenner-Fiedler. I'm your host, Jeremy Schubert. Each week, we discuss technologies used in automation. This week, Gil Guajardo, Product Marketing Manager for electric products, and Jerry Scherzinger, Product Marketing Manager for pneumatic products, both from Bimba, are here to discuss how close is close enough and what kind of positioning accuracy would you expect out of a pneumatic actuator versus electric. So with that said, guys, can you take it away? What are kind of our options for for actuators going from pneumatic to on up to maybe highest accuracy from an electrical standpoint?
Yeah, thanks, Jeremy. There's a couple of different ways to look at applications and solutions for applications that require multiple positions. Probably the simplest and lowest cost would be pneumatic cylinders. So I'd break pneumatics down into two classifications. There's conventional pneumatic cylinders that just have two stops. It's a hard stop at full extension, another hard stop at full retraction.
Okay.
And then once we start to talk about multiple position, that's when we can get into multi-position actuators, which the easiest way to think of those is kind of like one actuator stacked on top of another actuator.
Okay.
And when you utilize that type of an assembly, then you can get 3-position, 4-position, 5-position type actuators.
Wow.
They've all got different piston rod assemblies in them, and for each position that you would add another port to the assembly.
Okay.
So that's the easiest way to thinking about it. A 2-position cylinder, which most people are familiar with, 2 ports. We'll talk here probably most today about a 3-position cylinder that would have 3 ports. So that would be a full retraction and then a midpoint that it could stop at with a hard stop. That'd be position number 2, and then full extension, which would be position number 3.
Okay.
So that's an overview of pneumatic cylinders. And then once you get, the advantages to that design is it's very simple. It's relatively low cost.
Mm-hmm.
Once we get into other technologies, the cost goes up, but certainly the flexibility goes up as well. And the second one would be what we refer to as electro-pneumatic control. So it's kind of a blending of electric and pneumatic.
Okay.
I'm sorry, go ahead.
Yeah. So while we're on the multi-positioning, just some basics, just to make sure we've got a grasp on this. If you've got a 3-position, you've got 3 ports, you're just basically going to pressurize port 1 and it'll extend to position 1. Pressurize port 2 and it goes out to port the position 2, I guess, and so on.
Correct. Yeah. The easiest way to look at it is if we start from 0, which would be full retraction.
Yeah.
That's position 1. Then air into the second or the middle port, air into the bottom port, then strokes it out to the halfway point.
Okay.
Which is position 2. And then air into the intermediate port, strokes it out to full extension, which is position 3.
Interesting. Okay.
And then, air in the top port would bring both piston rod assemblies back to full retraction, and you're back to the home position.
That's very simple. So that's a nice solution. Is there an accuracy that people can expect, or, on that middle position, are they going to be within half an inch, or is it even better than that?
No, it's much better than that. And really the accuracy discussion, we should break down into 2 components, and that would be accuracy being one, but more important, repeatability being the second one, because that's really where you start to see some differences with pneumatic versus electric.
Okay.
So the accuracies would be the same accuracy as you'd find in any other conventional pneumatic cylinder, and that's really just based on a tolerance stack up of all the mechanical components.
Okay.
Typically, plus or minus 20 thousandths, plus or minus 30 thousandths, depending on whose cylinder you're using and what those tolerance stack-ups are.
Okay. Well, that's actually really good. That's a simple solution. You get 20 thousandths on 3 position. That's great.
Yeah, absolutely. And the big advantage is in repeatability because the pistons are stopping at a hard stop. In other words, the metal piston impacts the metal end cap. It's perfectly repeatable each time because there's no electronics involved. It's just a mechanical cylinder. When you put air to it, as long as there's nothing in the machine or the application that's going to prevent full extension, it's going to go to the same exact position every time. So that's really a great advantage to it.
Yeah, that's nice. Okay. Okay, cool. And so you were mentioning then the next potential solution is the blending, the electro pneumatic. How's that work?
Yeah, as a segue into that, maybe a final point on pneumatics is one of the disadvantages to that three position or multi position pneumatic cylinder is you're kind of stuck with whatever you specified.
Okay.
So if you order a cylinder with a stroke A of 2 inches and a stroke B of 3 inches, that's what you have. There's no
Yeah.
change in that unless you go out and buy another cylinder and physically replace the cylinder.
Okay.
The advantages in electro pneumatic and full electric is now those stop positions are configurable.
Hmm.
So now with, for example, with an electro pneumatic cylinder, what we're looking at there is it looks just like an air cylinder, but it's got a transducer built into it to provide position feedback.
Okay. Linear transducer in the cylinder.
Correct.
Okay.
There's a couple of different words for it. A lot of people call it an LVDT, which is a linear variable displacement transducer.
Okay. Yeah.
For most people, think of it a lot like maybe like a rheostat that's in a radio or the dimmer switch on your lights. It's the principle is you apply a voltage across this transducer. We'll say 10 volts for the sake of simplicity. And then as the cylinder moves under air pressure, it's still at its heart an air cylinder. As it moves with air pressure, it moves a wiper across this big resistor.
Okay.
So at say we had a 10-inch stroke cylinder, if you put air into it and you were watching a voltmeter, you would see the voltage rise from 0, 1, 2, 3, 4, 5, up to 10 volts when it's fully extended.
Gotcha.
And what that does is now we've got feedback. So we can take that feedback and put it into a PLC or put it into a digital readout device or anything that gives us feedback of the position. And that's the cylinder piece of electro-pneumatic control. And the electronic piece then is the fact what you do with those signals. So you can have a PLC set up. Say you're going to run, say you're positioning the rails on a conveyor, for example, and you want to run big boxes of cereal this morning and you want to run small boxes this afternoon.
Yeah.
You can pre-program in those voltages that you want to see back from the cylinder. So if the big boxes require a 8-inch span, then in your PLC or your computer, you want to extend that cylinder until it feeds back a voltage of 8 volts.
Okay.
When all you're done running all your big boxes of cereal, and now it's time for shift change, and you're going to change to a smaller box in the afternoon, electronically or with a push button switch or however you want to do your controls, you can just hit that button, and now we want to go into the small boxes, and we may be looking for only a 5-volt feedback.
Okay.
Cylinder will extend till it sees 5 volts.
So I imagine that now you got to have a way to control that position, right?
Right. I mean, the product itself lends itself to open or closed loop control.
Okay.
Closed loop control is probably what you're referring to a little bit then, and that's when the two big applications are either measuring and gauging type applications where you just want the cylinder to extend and provide a readout, quality control type applications.
Okay.
The other one would be pure positioning, and that's where you want this cylinder to act such that you want it to go out to 3 inches in return. Maybe next time you want it to go out to 4 inches in return, 5 inches in return. And this is all built into logic many times in a PLC.
Okay. Gotcha. So the PLC is going to read what position it's at currently, and then is there a special valve that you need to control the cylinder then, or are you pulsing a standard valve on and off?
Well, there's a couple different ways to do it. We sell as a package with the position feedback cylinder a product called our SPCS, which is our Servo pneumatic control system.
Okay.
And that's the valve and the electronics built into that SPCS.
Interesting.
Yes. So with the SPCS, it's taking 2 voltage. It's taking the desired position, whether it be 5 volts or 3 volts or 7 volts, and it's taken the feedback voltage from the cylinder, and it's comparing those two, and it's trying very hard to get to this equilibrium point by opening and closing the appropriate valves within this SPCS that Jerry mentioned.
Interesting.
And what it's going to do is attempt to reach this equilibrium point. And what's nice about that is you can essentially achieve an infinite amount of points between the minimum and maximum because the feedback that it's receiving and the signal that it's accepting. It's a analog signal between 0 and 10 volts.
Okay.
And because of that, it can give you a very fine resolution, and it can position that pneumatic cylinder anywhere in between and do it very well.
So your PLC would maybe have an operator screen connected that says we want to go to this position. The PLC then outputs a voltage to this SEPS. Is that what you guys?
SPCS, yes. So
okay.
it could be a PLC. It could be any type of device that's capable of providing an analog voltage. So it can be a digital panel meter. It could be a temperature controller. It could be a PLC with an analog card.
Okay.
It could be just a potentiometer of some sort.
Okay.
As long as it doesn't know the difference. It doesn't know what the origin of that signal is, other than it needs to be an analog signal. It doesn't really care what that something is. So there's a number of different options that it could be. The key is that it's that input signal is the desired position, and the feedback coming from the cylinder, the feedback cylinder, is telling it where it's at, and it's going to work very hard. The valve's going to adjust itself, open and close appropriately to allow it to position itself in the right position.
That's a really interesting solution. So what kind of accuracies or repeatabilities are we looking at with that? Since now we've got pneumatics and we've got closed loop, it seems like maybe you can get both, or what do you guys think?
Yeah. So one of the pros about the pneumatic motion control is that it's accurate to about 10 thousandths of an inch.
Wow.
And it's some of the other important advantages for this electro-pneumatic control is that you can get the characteristics of a pneumatic. So the pneumatic advantage over electric, bore size being the same, comparing kind of apples to apples, is that the pneumatic is capable of a lot more force.
Yeah.
So because of this control, it's kind of the best of both worlds, the electro-pneumatic control. It achieves many of the characteristics of pneumatic, the high force, the high speed, while approaching some of the accuracies and certainly the positioning, the infinite positions that you might find, or you do find, in an electric solution. So it's kind of the best of both worlds, and it's a real nice solution because it gives you characteristics of pneumatic and characteristics of electric all in one package.
Okay. And so I guess compare that then, while we're there, on to a full electric solution where you've got maybe a screw-based actuator.
Sure. Sure. Yeah. So the next kind of positioning tool we have is a electric actuator with a stepper motor driving it, and there are many advantages of that. One of the advantages is that you can achieve infinite positioning with this, and you can do it very, very accurately because of the characteristics of a stepper motor. A stepper motor will rotate a very precise angle. Most modern-day stepper motors will rotate 1.8 degrees for every pulse that they receive. And there's something called micro-step emulation, where you can essentially make that finer control to something less than 1.8 degrees. 10 times better is 0.18 degrees per pulse. So because of this micro-step control, the user, the control engineer, is capable or able to send a very finite, well-defined pulse train to the stepper motor and expect that the stepper motor will rotate in turn very precise amount of degrees or rotations, if you will.
Mm-hmm. And
because of that, the stepper motor is a very, very accurate way to control position. And it has other characteristics that make it a great solution. One is that stepper motors, generally speaking, are used without feedback. There's no feedback. They're open loop, they'll call them. And because of that, makes them a little bit less complex, since there's no encoder feedback. There's no encoder with them. In that situation, it becomes as simple as providing an appropriate amount of pulses, and then having the appropriate rotation of the motor shaft for those pulses. So that's a benefit of it. It's also compared to some of the other electric motor solutions for driving it. It's also probably the least expensive way of achieving position control and doing it very accurately. But at the same time, if you want to increase the reliability for a stepper motor, which is very reliable to start with, you can add an encoder. So you can add feedback to the installation. And so oftentimes you'll find control engineers adding an encoder to a stepper motor, using it with feedback. And the advantage here is that you can assure very reliable positioning without fear of misstepping, if you will.
Sure.
Because the encoder will be judging it, following it, and basically making certain that the position that you expect is the position that the motor shaft is in, and hence the rod of the electric actuator.
So what kind of positioning in general could somebody expect with a stepper-based actuator? Are they going to be?
So it's a function of many different of aspects, but generally speaking, one could expect to get positioning down to 1/1000th of an inch and do it very reliably. As I mentioned, to ensure that, the encoder helps a bunch, but again, you can run an electric actuator with a stepper motor without an encoder. The caveat there is to make certain that the load is a load that the stepper motor is capable of moving, and so in other words, that the electric actuator is sized right, and that the load itself that it's been coupled with is one that is fairly static. What I mean by that, it's not constantly changing and more importantly, increasing, whether it be speed or whether you have a heavier load. If your load is one that's fairly static, then a stepper solution is a good solution.
Okay, so that probably leads into the next option, which would be a servo-based actuator. And it sounds like dynamic loads, this is where you're going to go. Are there other benefits from an accuracy standpoint, or what's the quick overview of that?
Yeah, so with the servo motor, you're right, absolutely right, Jeremy. As to achieve a higher level of precision, a higher level of repeatability, of reliability, the servo motor is a good answer, and it's especially strong when you have a load that is in fact dynamic or can be dynamic, or when speeds are changing, when loads can be expected to be changed.
I've seen some maybe like bending applications where as you bend it, there becomes more and more resistance back to the actuator. Is that something that may be a better fit for the servo, since you've got this kind of dynamic load? Is that?
Yeah, that's correct. You're absolutely right. That's a good example of an application that would be served well by the servo motor. The thing about a servo motor compared to a stepper motor is one of the important characteristics is the performance graph, the torque versus speed, if you will, of a servo motor. And the thing about a servo motor, the extra advantage that is offered that you don't find in a stepper motor is due to the construction of the servo motor and the algorithms in the servo drive that's controlling that servo motor, is that you essentially have two performance graphs that you don't see in a step motor. And one is the constant or continuous current, and then there's another graph that's called the peak current or the peak performance. And the peak one is there to do exactly that during times of changing load, dynamic load, or during time of acceleration. It's able to give you short bursts of energy and more torque and hence more speed. That allows you allows the electric actuator to better adjust for these dynamic changing loads. And in that sense, it's a characteristic you won't find, which makes a servo motor even a better, more reliable solution.
Okay. So it sounds like in terms of accuracy, we've got, in just accuracy, not repeatability, we're kind of going up from the multi-position being the lowest accuracy, lowest number of points, electro-pneumatic, higher accuracy, as many points as possible. And then with stepper and servo, much more accurate, more points, basically an infinite number of points, and then your difference there coming in and your type of load. But I want to go back to Jerry. You mentioned the repeatability for the multi-positioning. Is that someplace where there's a big benefit from the pneumatic over the electric?
Yeah, certain applications require, virtually 100% repeatability. And that's really something you can only get in the mechanical world. It's much harder to get in the electrical world just because of the anomalies that come with electric signals, noise on the signals, things such as that, whereas none of that's a factor in a mechanical device when you're making a hard stop between two hard surfaces.
Yeah, okay. I can see, typically you control a servo motor, you're controlling the position of that shaft, but that doesn't necessarily always translate into the end of the actuator perfectly. Whereas a cylinder, you've got that hard stop you mentioned before, correct?
Correct.
All right, cool. Well, gotcha. Well, guys, thanks a lot for coming in. I think that's a good overview, and I think there's especially a good. You don't always have to go from a standard cylinder to I need infinite positioning. I need an actuator, electric actuator. I think it's a great overview. So.
Yeah, I think what's most important is that to understand the application and how close is close enough, just like we were talking about, because in many situations, the multi-position pneumatic is the best answer. It makes the most sense. In some cases, it's the electro-pneumatic cylinder. Other cases, it could be a motor with or without an encoder, or even a servo motor solution. It all depends on what the application calls for. Whichever one solves the application to the requirement is really what judges it and is the best solution.
Gotcha. Yep, I couldn't agree more with that. So, but that's I think you guys. I think that's finishes out this week. So thanks, Jerry, and thanks, Gil. Appreciate your time.
Thank you,
Jeremy, thanks for having us on.
Yep. And thanks to everybody listening to Brenner-Fiedler's This Automation Life. If you have any questions about what you just heard, or if you have a topic you'd like to hear discussed, please email us at tech@brfa.com. That's tech, TECH, @brfa.com. And be sure to continue tuning in each week. Thanks.